So whenever we see a rainbow like this, it's because radiation is being separated into its different wavelengths. We call that dispersion. The official term for that is dispersion, where the light is actually being separated into the different wavelengths, which means different colors. Dispersion. And a prism is used to separate the components, so used to disperse. So white light will produce a continuous spectrum. But some emitters of light radiate only certain colors and wavelengths. This produces a bright line spectrum. The various gases at low pressures are put into tubes and a high voltage is applied, and they glow in various colors. So they're just taking pure gases, putting them into little tubes, and then they're putting high voltage through it. It will now emit some kind of light and some kind of color. Sometimes it could be UV light, sometimes it could be infrared. It doesn't have to be visible light, but it will emit some wavelength of light. We can now measure that wavelength and use it to identify the color. I'm sorry, not identify the color, identify the element or the compound. So if the light is passed through a prism, a series of lines of colors is produced, and this series will now identify the element. Here's a nice little picture where the lines, I have the tube that I had before, and it will be jolted with some electricity, and then it will pass through a tiny slit just to narrow down all the photons. And then as the photons are narrowed down and they move through the prism, they will now be dispersed into different colors. And they will now produce single lines here. And if you can identify the element based off of these single lines. Every element has its own little fingerprint set of lines that we can actually use to compare in the future. Here are some examples of bright line spectra, and you can see that hydrogen doesn't have too many lines, and helium has a few more. Lithium will have just a few, but they're all in different places. They're all unique to that element, and they're all very special. Xenon has quite a few of them, quite a few. Some of them are there, and they're not really ever actually blurry, because remember, light is quantized. We only have exact numbers of wavelengths. There's no infinite number of wavelengths. There's only an exact number of wavelengths. That's what quantized means. And if you are really confused whenever I say quantized, then don't worry about the quantized model too much. That's not a huge tested concept in AP chemistry. That's more of a physics thing. So just relax if you're not understanding what quantized means. So Niels Bohr was able to use this was able to use the bright line spectra to make his Bohr model of what we had. And I showed you a picture of it in the previous video, and I'll explain a little bit more in another video where I'll show the more continual lines in a model. What he was proposing is that the electrons were only the hydrogen electron only travels in certain orbits. He picked hydrogen because it's the most simple one, and he could limit it down to one electron. There's only one way that one electron is working with, and this is the only one that he could actually do. He could only work with hydrogen. So all he did was look at the energy differences in those different lines, and was able to come up with his model. He looked at the energy differences between orbits and predicted wavelengths and which lines would be found. His research worked great for the hydrogen atom, but did not work well for any other atom or polyelectric atoms. So when he studied the energy differences, he used a couple of terms. He used the ground state, but he also used the excited state. Excited. And I don't mean that this electron is full of joy. I mean that it is at a state that it's higher than the ground state. That's what I mean. But it's fun to think of it as an excited electron. The ground state is the lowest energy level of the electron. Its actual smallest energy level is closest to the nucleus, and the excited state is any level higher than the ground state. It could be one level higher or 1,000 levels higher. So when we look at the energy levels here, we notice that the energy levels are not the same difference in energy from here to here. There could be a bigger jump from here to here, and then a smaller jump here to here and here and here. We're not exactly a pattern. Actually, there is, but we'll get to it. We'll get to it when we talk about orbitals, which I should have taught you in first year chemistry. That there's not every jump is the same. So if I were to draw another line here, it could be a higher difference in energy level. So it just depends on the atom, really. It depends on how close the electrons are. So what is going to happen is the jump from here to here is going to have a smaller energy than a jump from here to here is. So this has a lower energy. That would be why it's a red energy. This would be why it's red, because it has a lower energy. So it's a low. And then this one has a medium energy. That's why it's green. So this one is medium. And then the blue one is going to be a higher energy. So that's why it's higher. So I'm taking time on this one because this one is actually probably the most likely to be tested on the AP test. So this one's a good one to pay attention to, and I should have taught a lot of this in first year chemistry. And by rephrasing it, I did teach it in first year chemistry. I just hope you remember it from first year chemistry. So just remember that the change in energy is hc over lambda. That lambda is our wavelength. So that different wavelengths mean different colors. Just remember that. Howdy y'all, I'd like to show you how the model of the atom has now advanced past the Bohr model. You've gotten the Bohr model in previous examples of chemistry, and we've seen that the proton is in the middle and it's as the nucleus, and then the electron is orbiting outside. Most people accept this as the model of the atom as it is today, but as we've learned, it's not always that case. As I shine some light on it, all these different little orbs right here that are flying across represent different wavelengths of light. I'm basically shining white light on my box of hydrogen here, and so it's shining every possible wavelength on it. You notice what's happening to that electron. It keeps jumping to different energy levels, keeps jumping up to the different orbits. Every time it jumps up to a different orbit, I'll slow it down for you. Every time it jumps up, it's because it has absorbed some photon, and then when it jumps back down, it emits a photon. So watch it absorb again, and then it will emit, just like it did right there. It will now emit a photon at a specific wavelength. So this is the Bohr model and how it helps describe how light is. Now, de Broglie was able to come up with the wave model. So right here, it looks better when we look at it on a radio view, where it's not just a little dot anymore. It's an actual whole wave right here that's moving around, and the wave occupies the entire level. That's quite a crazy thing, and he figured out that the entire electron was a wave. Now, Schrödinger threw a whole bunch of math in it, and he finds out that there are several different orbitals that could exist. What an electron is doing is it's being excited to another orbital instead of another energy level. Instead of just another concentric circle, it's now jumping up to a different shaped orbital. This is a much better way to describe it, and the only way we were really able to figure this out was by using very complex math.